dB dt equals 1/5.
Yeah, so you want dB dt when what?
When b equals 40.
When b equals 40 compared to dB dt when
it's 70.
Correct. Basically, this is a, can you plug, do you understand, this is a reality check. It forces you to understand what you are looking at a most basic level.
Yeah.
So dB dt when b equals 40 is going to be 60 over 5, right? Yeah. And dB dt when it's 70 is going to be 30 over 5. So which one's bigger? 12 is bigger than 6. So again, though, remember though, you have to state the answer. You need to state the answer, right? So it's gaining weight faster when what? When b is equal to? When weight equals 40. Actually state the answer. Yeah. What kind of bird is this? It doesn't tell you, right? Well, they're grams.
A baby bird is
20 grams. These are grams. Not like the dodo or like an ostrich. Like, they're giving birth to orcas. You know, like, no. Find dB. What is? Okay, so d. Okay, so we have what, the second derivative in terms of time, right? So how do you go about finding that? What do we have to differentiate?
The first derivative.
Yeah, so you have dB dt, and we know that that's equal to what? 1/5 of what?
100 minus b.
100 minus b. So again, what is it asking? This is part B. It's asking for in terms of b. In terms of b. So when we differentiate this, what's a good thing to do first, Jesse? Jesse, what should I do first? If I want to take the derivative with respect to time, what should I do first? Real simple. What should I do?
Take the derivative.
Not yet. Just do. Yeah.
separate.
No. Just distribute first. I'm trying to get you guys to break this down just a little bit. Can you do this? Is that okay?
Yeah.
Or if you really want to, I know you guys like to do this. You could separate. But do we need to separate here? No, because we're not integrating. You separate when you integrate, right? So you have 20 minus 1/5 b, like this, right? So the second derivative with regards to time is going to be what? Negative 1/5 dB dt. Hey, is this like pretty much identical to the one we did like last week? Pretty much, right? You need it in terms of b though, right? So it's going to be negative 1/25 100 minus b. Is that correct? You have to take this right here, and where do you plug it in? Right there. Okay, so we did b. Then it says right here, it says, use the second derivative to explain why the graph of b cannot resemble the following graph. Use the second derivative to explain why the graph of b cannot resemble the following graph.
It has to be all the way concave down.
So yeah, so here's the thing. You have to go with what you definitively know about a graph. They're not going to expect you to like, it can't be based on some estimate of like output values. Because is this a very accurate graph? Like, do they give you fine details?
No.
But one thing you can tell is what Matt pointed out. What do you have right here? What do you know about on the green part from here to here? So the concavity is up right there, right? And then at purple it changes to concave down, right? When you look at this number right here, it seems to imply that there's a change in concavity, right? Yeah. So what does this say? We know that the second derivative with respect to time is going to be less than 0 when what is true? When what is true? We know it's going to... When b is less than 100 and greater than 0, right? I'm just putting it in realistic terms here, right? But the thing is, what's going on here? This implies that before it gets to an output of 100,
should be all concave down.
This implies right here that it should be all concave down when b is less than 100, right? Does everybody see that? But what does this graph show us?
It's concave up.
Change in concavity before what?
Before
it reaches before it reaches it, and it is b, reaches 100. Does that make sense? Mm-hmm. So in here the concavity changes when it's not going to. This thing is always concave down because the second derivative is negative before the entire time before it reaches 100. Does that make sense, everybody? Yeah. The second derivative, so it's always concave down. So a more accurate graph is going to look something like this, right? It's always going to be concave down and it's going to approach. Kind of with me so far? Yeah. Let's just do it, right? ln of, oh, the dB, thank you. So ln of 100 minus b is equal to what? Plus c. So what do we now know? E to the 1/5 t, e to the c is equal to what? And do you see what I did there? I just turned that in. So we've done this a bunch, right? So what do we have here? Usually you write it as what? A times e to the 1/5 t is equal to 100 minus b. This should be boring to you, right?
Yes.
But what do we need to isolate?
B.
We're trying to isolate b, right? So what do we have here? Did I do something wrong?
Yes.
What did I do wrong?
Chain rule.
The chain rule. What chain rule?
Negative.
Ah, thank you, because that's going to kick out a negative. Look at that. Good catch. So this is going to be, we'll do that as negative. If we had done this, it would have just...
I don't think it's a matter.
Hold on. Is it going to matter?
No.
You sure?
Yes, it will.
Hold on. You definitely did a negative outside there, right?
Yeah.
Definitely, right?
Yeah.
E to the C or A is going to...
So when you do this E thing, you have to get rid of all the coefficients out here. Let's do this real carefully. Do you see how easy it is to mess this up? I would like to pretend that that was on purpose. It was not. Okay? Totally owning up to my own mistake. You have to have the negative sign here. But before you can go from log form to exponential form, you have to get rid of all the things on the beginning, right? The coefficients in front of the log. So what do you have here? ln of 100 minus b equals negative 1/5 t. Now, does it matter if we make it minus c? Just make it, it's okay, right? Because it's a constant. It's going to do whatever it's going to do. Go ahead.
Well, it's simple like that. Do you want to just find out C?
You could, absolutely. That's a really good point. So what's your initial condition in this question? What does it say? B of 0 is 20?
Yeah.
Is 20? So what does that mean? When t is 0, b is... Sorry, when t is 0, the output is 20? So what do I plug in where I plug in? So it's ln of 100 minus 20 is equal to 0 plus c. So what do you have here? ln of 80 equals c. You can do that, absolutely. You could.
Yeah.
I don't. I like going to the end, personally. Because the only reason I like going to the end is I have to keep on writing ln 80 over and over again for a little while. I don't really want to do that. I like just going like this. Going, hey, it's going to be e to the negative 1/5 t, e to the c equals 100 minus b, like this.
Yeah.
I just like doing that personally, so that I can write 100 minus b is equal to a e to the negative 1/5 t, like this. So b is going to be equal to what? Negative a e to the 1/5 t plus 100? Yeah, because you have to subtract it to make it negative. Overall, it's the same amount of work. It's what you have to do with comfort levels. It's fine. 2012. Hey, a function g has derivative of all orders in the Maclaurin. They're even giving it to you. This is so nice. So nice. It says using the ratio test to determine the interval of convergence. Oh man, I get all excited when I see this. Nice. So do you remember the interval? You test the limit as we did this last week, right?
Yeah.
The limit as n goes to infinity of the next term over the current term, right? And you want that it will converge when that thing is what? Less than 1. Thank you. Good. Little stuttering there. Okay. So again, what are we doing here? We're doing the limit as n goes to infinity of what? The absolute value of what? an plus 1 over what? an. So that's going to be the limit as n goes to infinity of, what's the next one? It's going to be negative 1 to the what? Oh, I hate it when this happens. Snag editor. Negative 1 to the what? n plus 1. X to the 2 times n plus 1 all over 2n, wrong parentheses, sorry. 2 times what? I always have to do this out because is it really easy to miss one? Yeah. And I'm just going to skip a step here, and instead of doing the division, I'm going to multiply by the reciprocal of the original. Right? Is that okay?
Yeah.
I guess so, Mr. Seamon. Negative 1 to the n. And what is it? X to the what? 2n plus 1. Is that okay?
Yeah. Plus 3.
Is there a plus 3 in there?
2n plus 3, not 10 plus 3.
2n plus 3 on the top here. That is quite important. You're right. Okay, how are we doing on something? So again, what did we do here? We did this, and we have this nice interval conversion, but what do we have to check? So when you do this, you have to test it at negative 1 and 1. What does it show you? You literally, when you're doing endpoints, literally do it out so you can see it. So when you do this out, what do you see? First of all, it's alternating, right? And there's something you know about alternating series. You remember what you know about the alternating series test?
When the A goes to 0.
If an alternating series goes to 0, it converges.
Yes.
Is that true about all alternating? Is that true about all series?
No.
It's true about all alternating series, which go positive, negative, positive, negative. But if it's just going to 0, does that mean it's like the harmonic series? The harmonic series is going to 0, but does it converge? Does the alternate harmonic series go to 0? Yes. So both of these are alternate series. They pass the alternate series test, right? So therefore, does it contain the endpoints?
Yes.
So basically, they want you to do whatever the work we've done, test the endpoints, which is 1 point overall for credit, and then you have to bring all of that together to give an answer right here. Basically, that's the answer point. Be careful. That's 5 points. So don't think for a second. You might have stopped here and been like, oh, we're definitely done, because part of you might have thought, oh, it's only worth a couple points because it's part A. Is that true? No. Careful.
1/3.
Yeah, you're like, okay, 1/3 minus 5x squared plus 5 over 7x to the 4th minus dot, 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 dot. And then you just have to be careful here. When you take this derivative, right, you end up with what? 2n plus 1 times negative 1 to the n, right? You're dropping the power. That just sits there because the n is the general term. It's not actually moving. X to the what power? X to the 2n, right? Over what? 2n plus 3. There it is. You just have to do it really carefully. I'm about 98% sure that we're okay right now.
Is it sometimes easier to just get your own general term after differentiation?
Yeah, you absolutely could if you really wanted to. So look, they just write it out a little cleaner than this. Look what they give. How do you like this one? Oh, look, we're good. Yay. We got it right. What do you think the most common way is to mess this up? Signs can get messed up. You can start differentiating with respect to n and go berserk with some like quotient rule and be like, it must be hard, so I need to use the quotient rule. And you get something that looks like, and then you're like, no, it's not. A square. If I have a square,
I will.
kids, can you just listen? If I have a square, I want to prove this to you. It's actually algebra 2 is necessary. If I have a square and I fold it in half, which you know you can do perfectly because you have edges to work with. If I then take this point right there, that corner, and put it up there, do you remember what this looks like? I fold it up,
Yeah.
and what you end up with is it folds along like this line, and it looks like this approximately, okay? It looks like this, and I showed this to you before. So what do you end up with? You end up with, let me just get a little bit of this. Let me change, just let me do this line again. It goes to here, okay? So what does this look like? You folded across this dotted line, and what was really cool about it was that this point right here, this point, which you can get with 2 folds. You fold it in half, fold it back, and then you take this point and fold it up there. What was super cool about this is that this distance right here, this new distance, the distance from here to here, do you remember what was cool about it? This right here is 1/3 of the original side length of the square. So you've trisected a segment, which is really cool because it's not easy to do with like a compass and a straight edge, but with a square piece of paper, you can do it immediately. What's really cool about this is the following. If we say that, let's do this here. Let's say, for example, that this right here, this distance right here, let's call it this one, is A. Are you with me so far? We know that this length is going to be A because this side right here is the same as this one right here. Does everybody see it? You with me so far? I can't do a sideways highlighter, so that's why it's jagged. So if that's the case, can you tell me what the distance is from here to here in terms of if we're calling this square a 1 by 1 square?
1 minus
A. 1 minus A. Okay, we folded it originally in half. So this distance is A over 2. Are you with me so far? This is A over 2. Not A over 2, it's just 1/2. I'm sorry. It's 1/2. Are we okay with that? Okay, so what you do is you know that that's a right triangle, right? So you know that 1/2 squared plus 1 minus A squared is equal to what? A squared. You with me? Okay, so like, okay, 1/4 plus 1 minus 2A plus A squared is equal to what? A squared. What cancels on both sides? So you end up with 2a is equal to what? 5 over 4. And you're like, okay, this doesn't seem like it's getting anywhere though, right? Am I okay so far? Have I made any math mistakes? I don't think so. So what is a equal to? 5 over 8. You with me so far? So this is 5 over 8, correct? Well, we know that what's 1 minus 5 over 8? 3 over 8. So this is this length right here. So let me put this is 3 over 8, right? What's this one? 5 over 8, correct? Well, this is 1/2. What is 1/2? Look at the triangle. 4 over 8, 3 over 8. What is that? You multiply it by 8 because direct proportions hold with any triangle. So what do you end up with? A 3, 4 to 5 triangle. So with one fold, we constructed a perfect Pythagorean triple. I'll get the full diagram for this, but there's other really cool lengths in there. They're hidden all over the place. Like the exact, I think you labeled some of it. Like there's new distances. Like this distance is really cool because it's not it's not. I can't remember if it lines up or not. And then there's other lines that you can draw. Like if you start connecting these points, you start getting like really cool triangles. Think about that. That's 2 folds. We've trisected a line, and we have a 3, 4, 5 triangle. A method like this, I can't remember exactly what they said, but a method like this was used in ancient Egypt to like reportion land proportionally because they didn't have like giant surveyors, so they needed to minimize how they did things. Some pretty cool stuff. Anyway, I don't know what the lateral one is called, but you got an equator. What's it called? Prime meridian, right? Let's say you're standing right there. Yeah. And you walk straight north, right? Yeah. So Brenda, you're gonna walk straight north to get to the North Pole, right? You got it. And then you're gonna turn, and so you've walked this right here, and then you're gonna walk down like this, and then you're gonna walk back. Okay, you with me so far? Totally. This is 90 degrees. This is 90 degrees, and that's 90 degrees. Oh. You have walked a triangle, but what do those angles add up to? 90, 90, 90 is 270, right? Okay, what happens though if you walked a smaller triangle, like inside? The internal angles, are they going to add up to 270? No, less than 270. Oh, what happens if I walked a bigger triangle, meaning I stretch this point that way, I stretch this point back, and I stretch this point back? What happens to the internal angles with that triangle? It's bigger. What's the largest it can be? You can stretch all those points all the way around, and they'll meet at the back. 360. So on a sphere, the internal angles of a triangle go from 180 to 360, depending on the size of the triangle. Right? Isn't that cool? Oh, no! There are non-Euclidean geometric spaces where parallel lines intersect. And you're like, no!